And all. Welcome to the third session on design of steel structures. So in the last two sessions, we discussed on design of bolted connection and also welded connection problems, particularly with respect to the gate. So this time we'll go with design of beams. So we are know that if we adequately supported what the compression flange of the beam, then those beams we call it as laterally supported beam. The design strength of the beam, when it is adequately supported against lateral torsion buckling, okay, then the strength of the beam will be governed by yield stress. Whereas if not adequately supported against lateral torsional buckling, then it will be governed by the lateral torsion buckling strength. So this two we need to remember. So if it is adequate against lateral torsion buckling, then the beam will be governed by yield stress of the material. If it is not, then the strength will be governed by the lateral torsion buckling strength. And one more thing, if the compression flange is supported adequately, okay, then we call it as laterally supported beam. Otherwise, we call it as laterally unsupported beam. So when I go to the laterally supported beam, okay, when the factor design shear force, which is acting on the member, when does not exceed the 60% of the design strength of the design shear strength of the beam, then that case we call it as low shear case. Okay. So for low shear, if it is exceeds, so if V is exceeds 0.6 VD, then we call it as high shear case. So in case of low shear case, the bending moment, that bending strength of the beam can be calculated using this formula according to IS 800, MD equal to beta ZP Fy by gamma m naught, where ZP is fluctuation modulus of the beam, Fy is the yield stress, gamma m naught is a partiality factor for yielding, and also beta is the factor Zp by Ze. So next, for simply supported beam, the MD we should check with the MD whatever you calculate using this formula. We should check with these two criteria for serviceability thing, and also the factor design strength equal to area into stress of the material. Area is AV, yield stress Fy W divided by root 3 gamma m naught. Okay, this is what the shear strength and also the bending strength of the laterally supported beam when your case under low shear case, that is the design shear force does not exceed 0.6 VD. Okay. So then if you go for next thing, in case of beam, we need to know what do you mean by web buckling and what do you mean by web crippling. Okay. Web buckling is a localized deformation at toe of the fillet. So because of the concentrated load acting on the beam or at supports, if it is simply supported beam, at supports we're going to have more shear force, unbalanced shear force. Okay. So in this junction, we're going to get web crippling. If entire web will going to deform because of the concentrated load, then we call it as web. This is what web buckling. The second one, this first one we call it as web crippling. Okay. The web buckling dispersion angle we should take while calculating the strength, web buckling strength as 45-degree dispersion angle. Whereas for web crippling, we should take it as 1:2.5 dispersion angle. Okay. Next, if you go for some of the questions, previous year questions on the beams, the steel section is subjected to combination of shear and bending stress, bending action. The applied shear force V and the shear capacity of the section Vs. For such section, the high shear case. So just now we discussed for high shear case, the design shear strength, design shear force is greater than 0.6 or 60% of design shear capacity. So the capacity here is Vs. So if V is greater than 0.6 Vs, then it will come under high shear case. If it is less than 0.6, then we correct as low shear case. This 1 marks problem. Next, if you go for next question, generally the maximum deflection to span ratio of a steel member we should take according to the code as 1/325. Okay, in case of RCC, we're going to get 1/300. Here we should take 1/325. When the next question here is an ISMB 500 is used as a beam in a multi-story construction. From the viewpoint of structural design, it can be considered as laterally restrained. When it is considered laterally restrained beam, when you support or when you restrain the movement of compression flange completely. So your option B is the correct answer. The compression flange is laterally restrained. Whereas tension flange is restrained, that is not come under laterally supported. If it is compression flange restrained, then we call it as laterally restrained beam. Okay. The next question here is which of the following factors that does not affect the lateral buckling strength of a steel eye section undergoing bending about the major axis. So here the answer here is the option C. The radius of gyration about the major axis of the section, we should consider here the factor, the radius of gyration. So if you go for next question, the steel beam supporting loads from the force slab, and also as well as wall we correct as option A, that is stringer beam. Okay, whereas lintel beam will going to take only the load, in the openings. So spandrel beam will be a different one. Whereas if you consider, if you the beam is taking floor load as well as wall load, then we correct as stringer beam. Okay. The next question here is the designing of when designing of steel structures, one must ensure that local buckling in webs does not takes place. The check not be required, may not be very critical when using the roller steel section, the because here the depth to thickness ratio, the depth d by t ratio is maintained, is appropriately adjusted in case of roller steel section. That's why sometimes the checking is may not be required. Okay. The next question here is they're given different elements, and we need to check where we need to place those elements. List one contains uh, contains some elements in design of simply supported plate girder is something but a beam, and list two will give some qualitative locations of the girder. Match the items to list as per good design practice and relevant codal provisions. Okay. So according to this, so the where we need to give the web splice. So we need to give the web splice at at not at supports we need to provide strong web, so we need to provide so away from the center of the span. Why? Because so here we need to increase the bending moment capacity of the section. That's why we need to provide the flange. If you go for second one as a web splice, so B, here we need to provide. Okay, here we need to provide at one second, where place we need to provide it supports. So at supports we're going to receive maximum shear force or unbalanced shear force. So option 3, it will match with the web splice, whereas plan splice will be matched with away from the span. So third one, bearing stiffness. So stiffness are the one we're going to take the load. Okay, so bearing stiffness we need to provide at so that is at one, that is at supports we need to provide the bearing stiffness. Okay. So next one, the horizontal stiffness to increase the capacity of the the web portion, again we need to provide at the longitudinally somewhere in the compression flange we need to provide the horizontal stiffness. Okay. So here for this question, so to list for list 1 to list 2 mapping, so option A is the correct answer. So next is the adjoining figure shows schematic representation of steel plate girder used for simply supported beam with a constant load. So load, here you have the constant load. For stiffness, here they given two stiffness. The PQ is horizontal stiffener, RS is vertical stiffener. Okay. Okay, now where we need to place this? So they're asking whether the true condition we need to specify out of these four options. Okay, so here I will go directly to the answer. The RS is nothing but vertical stiffener. RS helps to prevent the local buckling of the weld. Therefore, we need to provide here. Okay, so here or anywhere. So the thing is, we need to RS. What is the property of the purpose of RS or vertical stiffener? To prevent local buckling of the web. Okay. When you go for the PQ, the PQ's horizontal stiffness should be placed in the compression flange side. So PQ should be placed near the compression flange side to take care about the maximum bending moment acting on the plate girder or the beam. Okay. Next question on beam. So just now we discussed the flexural capacity of the beam. This is what the formula is given in the code book. That is design capacity in bending equal to beta B ZP Fy by gamma m naught. If you go for this, the question, the semi-compact section of laterally supported beam of an elastic section modulus and flat section modulus, they given as 500, 600, ZE and ZP, and they given bending compressors also as a 200 MPa respectively. The design flexural capacity expressed in terms of kilonewton meter of the section is, so we should remember this formula. So this is a very simple formula, right? So MD is beta B ZP Fy by gamma m naught, where beta B is 1.0 for plastic and compact section. We know that according to the code. Whereas if the section is semi-compact, here if you observe the section is not compact, not plastic. Therefore, beta B we supposed to calculate. So the beta B will be the ratio of ZE by ZP. Okay, ZE by ZP. So now, so if you go for ZP, it is given. So what is ZP here? ZP is for 650. ZD is also given 500. Yield stress of the material is given. Gamma m naught is partial safety factor for material against yielding. So then if you substitute the formula, you're going to get this answer. So this is what the bending capacity of the beam. So here we need to express the answer in terms of kilonewton meter. Be careful here. So whatever the answer you're getting, we should substitute here in terms of kilonewton meter. If you substitute in Newton meter, so they won't award any mark here. Okay, answer here is 100 kilonewton meter. Okay. So next question. Next question here is they're given like this: the steel column ISHP is subjected to factorial axial compressive force of 2000 kilonewton. So this is a column question, that is a base plate question. So here this is a base plate calculation question. So subjected the load is transferred to the concrete pedestal of concrete grade M20 through a square base plate. Consider the bearing capacity of the concrete as 45% of FCK. Okay, the here we need to what we need to calculate here is using limit state method, neglecting the self weight of the base plate, the steel column, the length of the base plate should be. So here since they given us a square base plate, okay, the factor load will be bearing capacity of the concrete. Factor load is given. So this is the problem with respect to the bases, the concrete base plate or the steel base plate here. Okay, factor load divided by bearing capacity of concrete. So factor load is 2000 kilonewton is given. Okay, so the bearing capacity is 45% of FCK in terms of millimeter square. The base plate equal to square root of what the area required. You're going to get 47.14. We need to place nearest to the value. So 47.14 on the safer side. We need to provide 48 centimeter. This is what your answer for base plate problem. So then next, if you go for the important concept called plastic analysis. So I will go for the now. First, I will discuss the things with respect to the classification of cross sections based on moment rotation capacity. So the entire steel sections, what are available in the market or what are the people using, they can classify into 4 categories. Okay, class 1, class 2, class 3, class 4. Where class 1 we also call it as plastic section, class 2 is compact, class 3 is semi-compact, class 4 is slender. So if you observe for the class 1 section of the plastic section, the moment rotation capacity is more. Here you can observe here, this is what the moment rotation capacity. The capacity will be more. And if you observe, all the fibers have reached all the extreme fibers and also all the fibers from top to bottom. So above the neutral axis, below the neutral axis, all are subjected to a stress of Fy, reached maximum yield stress. So that's why this section we call it as plastic section. This is the section we're going to take heavy load. Okay, more it's having more strength. So and it will going to have the capacity to, the plastic section will have the capacity to formation of plastic hinge also. So we know that after the formation of the plastic hinge also, the member will going to take up more load. So that's why always we need to prefer the plastic. So when come to class 2 or semi-compact, here all the fibers are reached the yield stress Fy of the material, but the rotation capacity is much lesser than the plastic section. Okay, and also with respect to the plastic hinge formation, though here we won't get any plastic hinge formation in case of class 2 or compact section. Okay, but whereas all the fibers reaches Fy, the strength of this section is lesser than class 1. If you go for class 3, okay, so here if you observe, the extreme fibers are reaches Fy, the interior fibers not reach Fy, the yield strength of the material. Okay, this sections we call it a semi-compact section. Here there is no formation of plastic hinge since all the fibers they are not yielded to a maximum stress. So fourth one is class 4 section or slender section. Here this is the weakest section. What will happen here? So because of application of the load, because of undesigned depth to thickness ratio, okay, upon application of the load, the member will going to fail. So normally we will going to use for steel sections as a plastic sections we're going to use for the steel sectors. We'll go for one more element called compact. We will try to minimize the semi-compact also. Sometimes we'll use, whereas slender we avoid this type of sections for our steel structure usage, because this will have the local buckling failure. Before the application of the force, the member will going to fail due to local buckling. So the whatever the cross section I have discussed here, those cross sections can be classified here according to the width to thickness ratio, which is available in table number 2. So based on the compression element, the outstanding compression flange, internal compression flange, web of I section, rolled section for welded section. Okay, all those things they're given based on these ratios. What is these ratios? For compression fluid, they taken as B by TF ratio, that is width of flange by thickness of flange ratio, B by TF ratio, D by TW ratio. They will going to decide the web, the section whether it is plastic or compact like that. So if the values does not exceed these limits, that is 9.4 epsilon, 10.5 epsilon, 15.7 epsilon. So then based on this, we can categorize it as class 1, class 2, class 3. So they not given for slender sections. Why? Because we are not supposed to use the slender section for our steel structures, since it is susceptible for local failure. Okay. So next, based on that, the classification of cross section, we'll discuss one question now. That is the question on the classification cross section. Here they given the details like this. As per IS 800-2007, the cross section in which the extreme fiber can reach the yield stress, but not develop plastic moment capacity. So what is plastic capacity? So if all the fibers reaches Fy, what is compact? All the fibers must reach Fy. Whereas for semi-compact, only extreme fiber reaches Fy. Okay, then not able to develop a plastic moment. Then the answer here is C, semi-compact section. Okay, so we don't have any shear section like that. So only we have three sections here. So this answer is so semi-compact section, since only the extreme fiber reaches Fy. So then if you go for shape factor is nothing but the ratio of plastic moment, plastic section capacity, section modulus to elastic section modulus. So here they given a triangular shape like this. So for this, we need to calculate the shape factor. So we know the shape factor is the ratio of Zp by Zy, where Zy is the moment of inertia to the extreme fiber distance. If you take here the extreme fiber from this line, it is taken as H. Okay, Ixx we need to calculate about this line. So how to calculate Ixx? We have two triangles. So at the base, the value will be BHQ by 12 at the base. Since we have two triangles, they are taken as 2. 2 times of BHQ by 12, you're going to get BHQ by 6. So ZY is BHQ by 6. ZP is nothing but the plastic section modulus. What is the procedure to calculate plastic section modulus? We know this. The plastic section modulus we need to calculate always on the equal area axis, the axis which will divide the total area into two equal halves. So here the x axis itself acts as the equal area axis, right? So the above area and below area both are same. So therefore, how to calculate this? You identify the area. Okay, you mark here the central distance, that is y bar. So for the second one, the central distance will be y bar 2. Okay, so second element, this is first element. So then area into y bar plus area into y2 bar. So then 2 times of the, what is the area of the triangle here? Half into base into height. If you take any one of the triangle, okay, since the dimensions are same, you're going to get the same value, half into base into height. Whereas the distance from here to here, from this perpendicular distance, the h value will be, the distance will be h by 3. Therefore, your answer is bh square by 3. If you substitute to this formula, that is shape factor formula, Zp by Zy, you will going to get the answer as 2. So for this, the figure, the shape factor here is 2. So I will brief now how to calculate shape factor. Shape factor is nothing but the ratio of Zp by Zy. Okay, Zp by Ze, elastic modulus. So Zy or Zx, we need to decide. That is both are under comes under elastic modulus. We need to decide when we need to take Zy, we need to take Zx. So here they are taken as Zy, since we are calculate since the metal is resting on vertical plane. Okay, so this is what your Zy. So in Zy again we have the formula, moment of inertia. The elastic modulus will be moment of inertia divided by extreme fiber distance. Okay, so whereas in case of plastic section modulus, the area we should take as half area into y bar and half area into y2. So this is what the procedure to calculate the shape factor. This is a very, very important concept. So they will going to ask frequently 1 or 2 marks question from this concept. So next, one more question here we have the shape factor. They given different elements. We need to place the increasing order. So if the shape factor of the material is more, obviously the strength of the material will be more. Okay. So now if you see here, for the circle, we should remember this, the shape factor will be 1.67, for diamond 2.0, for I section 1.5, and for rectangle 1.5. So now if you want to give in increasing order, diamond we should give that as a first place. Okay. So diamond. So then where is, one second. So we need to place in increasing order. So first one I need to put the least one, that is option 3 here. Okay. So next the dimension, this diamond will be in the first place. Okay. So third one is 1.5, that is I section. So next fourth one is rectangle, again that is also 1.5. So first one is circle, that is 1.67 greater than 1.5. The last one is 2. So I need to place here in increasing order. Therefore diamond will come in the last place. Okay. So now again, if you see here, there are so many questions on the shape factors. You need to remember for basic, geometrical shapes like rectangle, I section, diamond, triangle, and also circle. Okay. So now I will go further with this question. The shape factor, shape of the cross section which has largest shape factor. Just now we discussed which one is having largest shape factor, the diamond shape. Here you see. Okay, so out of this rectangle, I section, solid, circular, diamond will have larger shape. The shape factor rectangle is 1.5. You should remember this value. Okay, so these are some of the shape factors. So if you see here, the triangle is having highest shape factor when compared to diamond. So now if you remember how to remember this, the highest will be for triangle, the second one will be for diamond, the third one will be for circle. Okay, the fourth one will be for rectangle, the later I section. So actually, so if the shape factor of the geometrical section is more, the more will be the strength of the material. So it will going to take more load. Okay. So actually we need to provide for our building or any shape. If you go for triangular shape, so you're going to end up with more strength of the design strength of the element. Okay. So but because of some farmer problem, we'll go with rectangular shape. So again, this is also a question based on the calculation of what the S value and MP value. So here Z value and MP value. S is nothing but shape factor. We know how to calculate shape factor. Shape factor is nothing but MU by MI, MP by MY or ZP by ZY. Okay, just we need to calculate first ZP. We know ZP half area into y1 bar plus y2 bar. Here if we, on this line we can divide equally off. So from this here, this is what y1 bar, this is what y2 bar. Okay, so here what is the the area here, half into base into height. Okay, so here they have taken the area, total area here. So since it is a square section, they have taken total area by 2. Actually, the ZP concept is total area by 2. So if you want this area, half area, you take total area by 2. What is total area for square? 100 into 100. By 2 means we're going to end up with half area. Half area into this y1 bar or y2 bar. This one we should calculate. So the y1 bar will be 100 by 3 root 2. Here also 100 by 3 root 2. So ZP you can calculate here. So again you calculate MP. So later the MY value you can calculate directly like this. So for MY, FY into ZP. Okay. So FY is 250 for the material. Okay. ZP we should calculate here I by Y. If you calculate I by Y, you're going to get AQ by 6 root 2. So this is what your MP. So then if you take the ratio of MP by MZ, you're going to get the shape factor as 2. Okay. So next, this is one more important problems on plastic analysis. Okay, so I will discuss in detail this first problem. A proper cantilever beam, as shown in figure, the plastic capacity of the beam is MP. So what is the collapse load? So here in the exam, they will going to give the different types of beams. Okay, so they will ask for the moment capacity or the plastic collapse load. So the thing we need to remember here is, if this is a beam problem, yeah, this is what your fixed support, this is what the roller support. So first we need to identify where the plastic hinges will going to form. Okay, where the plastic hinges will going to form? The plastic hinges will going to form where the fixed support is there. So in this case, fixed support is there on the right hand side. So here only we're going to get the plastic hinge. So whereas in roller, at roller or at hinge or at simple supports, we won't get any plastic hinge formation. So that one we should know. So what is the first one? So first one is the concept, the plastic hinge will go to form only at fixed end. Okay. The next important thing is the plastic hinge will go to form whenever we have the change of cross section. So plastic hinge will go to form whenever we have change of material between the section. Okay. So fourth one. So when they will going to get plastic hinge, whenever we have the point load under the maximum load, under the load we're going to get the plastic hinge. Now, if you take this cantilever example, cantilever beam example, on the left hand side we have roller support, on the right hand side we have fixed support. I can decide directly here. I will not get any plastic hinge here. Okay, at simple support, I will get 1 inch at fixed support and 1 inch under the load. So here they have taken this mechanism we should write. Okay, so now here this is what the mechanism, the different shape of the beam. Because of this load, the here under the point load, we know the plastic hinge will go to form here. So at fixed end also one more plastic hinge will go to form. Okay. So then I need to write the plastic moment capacity. So only whenever you have the plastic hinge, then only you will going to get the plastic moment, not here. Here the moment will be equal to 0 because of simply supported condition. Okay. So this moment will going to act like this, so it has to pushing the element to its original position. Okay, it has to act like this in this clockwise, in here anti-clockwise, here clockwise, here also anti-clockwise direction. What is the writing anti-clockwise direction? The beam is pushing back to its original position, that's why. Okay, but now we need to calculate external internal work done, and both external and internal work done. If you go for principle of virtual work, so this component we call it internal work done. Internal work done is always the multiplication of moment into the rotation. Here we have the rotation at this junction, where at this support, but we don't have moment capacity. Therefore only here we need to concentrate this junction and also this junction. Okay, so here how much internal work is there? MP theta, so this portion. Okay, next is this MP theta. Okay, so here at inch we have one more MP theta. Therefore your answer here is for internal work done 3 MP theta. Okay, so on the other side, that is external work done, we should take as load into deflection. So how to calculate deflection? Deflection, this is what your beam. Okay, so this is what your deflection. So this is what your L by 2. This is also L by 2. This is what theta. This is also theta. So if you go for tan theta, what I want delta I want. If you go for tan theta, opposite by adjacent is L by 2. So since theta is very small, that tan theta becomes theta. Therefore delta becomes theta into L by 2. That's that is the thing they are written here. So this is what your delta. So force here is P. So delta is deflection. Okay, P into L by 2 into theta. So now if you substitute here, if you equate according to principle of virtual work done, you will go to get P as 6 MP by L, nothing but collapse load equal to 6 MP by L. Okay, so in these problems what we need to do, first we need to identify where the plastic hinges will go to form. So where the plastic hinges will go to form? At fixed ends, at change of cross section. Okay, and at change of material and under the maximum load. Later we need to write the deflected shape of the beam. So we need to write the MP wherever we have got hinges. Okay, so then we should calculate the internal work done as moment capacity MP into rotation theta, and external work done as P into deflection, nothing but load into deflection. So this is a 1 marks question. So for the proper cantilever beam, this is a proper cantilever beam, correct? For proper cantilever beam, when the load is acting, the constant load is acting in the middle portion, then your collapse load will be equal to 6 MP by L. So you should remember this. So next, if you go for next problem, okay, so this is fixed beam. Okay, fixed beam. So here we have P acting at center. We can go with this is also static method. Otherwise, you can go with the previous mechanism method also. So then what you supposed to do here is, so you write the deflect shape. If you take this example, so this is what a P, this is what a fixed beams, right? So I will go with a previous similar to previous one. So you should write deflection shape like this. Here also, since it is fixed end, you will go to get 1 inch. Here also 1 inch. Here also 1 inch. So this is delta. So since P is actually exact delta by 2, sorry, L by 2, your delta becomes L by 2 into theta, exact similar to previous problem. Okay. So now the internal work done will be equal to MP theta in P theta, MP theta, MP theta, 4 MP theta. Okay. So external work done will be equal to P into delta, nothing but L by 2 into theta, 2 into, if you come to this side, 8 MP theta equal to 2L theta, theta will go to get cancelled. Okay, so then your plastic load will be 8 MP by L. So this is what the mechanism method, or this we call it a static method. We can also use this method. Also better you go with only one method, that is the mechanism method. Okay. So now, when you go with next problem, now we need to identify where we're going to get the plastic hinge in a beam. So we already know the plastic hinge form at fixed ends, the plastic hinge form under the maximum load, but here the given condition like this: the steel beam with constant EI span L is fixed at both the ends and carries uniformly distributed load, which is gradually increased till the beam reaches stage of plastic collapse. Okay. Assuming B at midspan, assuming this B point at midspan, which of the following is true? So now in this problem, we need to tell if the beam is having constant depth and I section I value. So we need to tell, okay, where we will going to get the hinges, whether at A, at B, at C, where we will going to get first hinge, where we will going to get later hinges. So here the answer here is, okay, for this problem. So initially the load will increase to maximum negative bending moment will occur WL square by 12. We know this. Okay. So then first what will happen? First 2 hinges will go to form at A and C. So at fixed end moment, at fixed end, since the moment is heavy, the plastic hinge first will, instead of under the load, it will go to form at supports, that is at A and also at C. Okay. Then the third image is going to form at under the load. So the thing here is, whenever they ask it like this, we should calculate the maximum fixed end moments for supports and also the maximum fixed end moment for the load condition. So based on the quantity of the loads, we can tell where we're going to get the hinges first. So this is one more problem. Again, the proper cantilever beam. We already know this problem, correct? So the first problem I discussed, the carrying vertical constant load acting on the midspan, the plastic moment capacity is MP, the magnitude of collapse answered by default is 6 MP by L. So here, so this is what your prop fixed end. So moment here we have moment. So 2 MP theta, 2 MP theta, finally we're going to 6 MP by L. This is exactly the same problem of the first problem what we discussed on plastic analysis. Okay. The next one, a cantilever beam length L width B depth D loaded with constant vertical load. Okay. At the tip, the yielding stress starts at P. From it starts at P. What is the collapse load? So now we need to calculate the collapse load. So this is the condition they given, the P and also the cantilever beam condition. So we know the maximum bending moment will be P into L. Okay. So now if you go for MP, the plastic moment capacity, the value will be collapse load. So always for plastic capacity, always we should consider the collapse load W into L. So now we know the shape factor is MP by My. So this is what is shape factor MP by My. For rectangle, we know this. This is standard value 1.5. If we equate these two here, for WL by MP by L, if you equate to 1.5, then you're going to get collapse load as 1 times of the P. Whatever the load acting on the beam, okay, whatever the load acting on the beam, the collapse load will be 1.5 times of P. So next, so this is a lengthy problem. So this is 2 marks question. Why? Because they given 2 point load acting on the proper cantilever beam, whereas in the previous one it was only one force acting on the beam, proper cantilever beam. Here what we should do, we should go for beam mechanism. First I will identify where the plastic hinge formation will going to occur. So we know that one at at hinge, one at under the point load, one more at under the point load. Here we won't get plastic hinges because since it is simply supported. Since what I am supposed to calculate here is, I need to go with a mechanism 1 and mechanism 2. Okay. So first mechanism I can go with by considering this load. Second mechanism I should go with considering this load. So okay. So load, that means deflection under those loads we should supposed to consider. So if you consider first case, okay, here they consider here the deflection under this load. Okay, here they written the mechanism like this. Here also MP theta, MP theta. We should calculate carefully that this what I want finally. I want this deflection. Deflection we should calculate carefully by using these two triangles. Here here the rotation they taken as theta. Here they taken rotation as alpha. So here they calculated the relationship between theta and alpha. So wherever you have theta, we can substitute as 2 alpha. Wherever you have alpha, you can substitute theta by 2. So first case, they consider the load under this, deflection under this load. So then internal work done will be the external work done will be like this. The internal work done will be this one. So if you equate these two, okay, then you will going to get first case, the collapse load will be 5 MP by L. Okay. For second case, they have taken the load or the deflection under this load. Okay. Under this load again here we need to calculate the relationship between this theta and alpha by considering this as delta. Okay, delta is where in the previous case delta is we are taken under this load, in this case delta we taken under this load. So based on that, alpha equal to 2 theta, again you calculate similar to the first problem, external work done and also internal work done, you're going to get the collapse load. So out of this collapse load, okay, the least collapse load will be 4 MP by L. If you apply 4 MP by L, the beam will go to collapse. So out of these two mechanisms, 5 MP by L and 4 MP by L, the least value is 4 MP by L. That is what your answer, option B is the correct answer. So next is again the beam. This is a proper cantilever beam, but in this problem they given some distances. No need to worry. Just you calculate the delta here. Okay, you calculate what is that relationship between this rotation and also this rotation by considering this as a reference one delta. Okay, you can consider this triangle and also this triangle. You calculate the collapse load. Your collapse load will be here for this problem. This is exactly similar to the first problem. Here also we need to calculate internal work done and also external work done. Okay. So now your answer is 13 by 21 MP. So option D is the correct answer. So next one, here is we need to take negative work done. Here, since it is overhanging case, okay, here we won't get any plastic hinge here. Okay, since it is simply so, here also we won't get any plastic hinge here. The final thing is we should calculate the collapse load. So this is what your mechanism part. Only under the load we will going to get the hinge portion here, the plastic hinge. Therefore MP. The internal work done will be MP theta and MP theta. Whereas the internal work done, we should take here the negative MP, since it is the work is the since the beam is deflected above the reference line, we should take negative work done here. So your answer again comes out to be exactly similar to 6 MP by L. So next problem is an important problem here. The formation of plastic collapse mechanism, they're given like this. Okay, the PU will be CMP by L. So we know always the collapse load will be some value into MP by L, some numerical number. Here we should calculate what is this numerical number. Okay, so here they given the section like this. We know at fixed section we will going to have what are the fixed, the inch. At change of cross section we will going to form an inch, and here also we will going to get 1 inch. So it since this beam is change of cross section, I need to go with the two types of mechanism similar to the previous problem. First mechanism will be like this. Okay, so here I'll consider first the inch formation at supports and also 1 inch formation at center, like this center of change of cross section. So if you take here, but always we should take the deflection under the load only, not at here. So not at change of cross section, deflection always you should take under the load. If you calculate the internal work done like this, here we have 3 MP, here they given for this section as 3 MP at this junction. So at this junction, so since there is a change of cross section, on right hand side we have MP capacity, on left hand side we have 3 MP capacity. At this junction we should take the least value between 3 MP and MP. So out of 3 MP and MP, so MP is the least value. Okay, here they are taken as MP, 3 MP. Here also at this junction we should take MP. So this is what your external work done. Internal work done will be load into deflection. Your answer is 6 MP by L in this case. Okay. So if you go to beam mechanism 2, so then we should consider in this mechanism the inch formation at the supports, both the fixed supports, the right hand side and left hand side, and also under P. So this is what your fixed inches. Here also you're going to get inches. Here we should calculate delta here. They taken the rotation here as theta. Here they taken as phi. Later they come up with a relationship between phi and theta. So then you calculate P, collapse load. If you calculate collapse load by considering what the internal work done and external work done, here when you come to here, what will happen? Here at this junction we have only MP, not 3 MP or 2 MP. Therefore here 3 MP, MP theta, MP theta, MP theta. So if you equate those two, finally you're going to get answer as 10.33. So your answer for C, the constant 10 by 3 will be 3.33. Therefore, from this answer, the denote the plastic capacity, the beam section as the value of C will be 3.33 is the correct answer. So the least value we should write. So next, this is exactly similar to the previous one. Just now we discussed. Here also we have two mechanisms, right? Two mechanisms. Okay. So here they given load here, whereas in the previous problem they given load here. Okay. The thing here is we should take we should calculate carefully the alpha values, the theta rotation values. Okay, the deflection values. So again here also we have two mechanisms, fixed ends and also change of cross section one mechanism. Okay. So next, fixed end and under the load one more mechanism. So based on those things, we should calculate the MP values. So out of two MPs from mechanism one is it is 16.5 MP by L, from mechanism 2 15 MP by L. So out of these two, the least value is 15 MP by L. Therefore, your answer is 15.5. Sorry, 15 MP by L. Option C is the correct answer. So this is exactly similar to previous problem again. Okay. So fixed end beam, here the distance is 2L by 3, whereas in the previous problem they given us L by 3. The thing here is it will take, we need to carefully calculate the deltas and also the MPs, that is plastic capacities. Okay. So at this here also we should take as one mechanism as the supports and also the under the load one mechanism. One more mechanism will be the supports under the change of cross section. So if you calculate separately, you're going to get like this 8.25 MP by L and 7.5 MP by L. Your answer here is the least value 7.5 MP by L. Okay. So next thing is one more problem I have taken directly the calculation of safe factor. So here they given I section. Okay, I section here they're asking the plastic section capacity. Okay, modulus about weaker axis. So about weaker axis is nothing but so about y axis, about this y axis. About this y axis, we should calculate the plastic section capacity. So we know that plastic section modulus is always area by 2 into x1 square x bar square plus x2 bar, nothing but the distance from the this weaker axis to the center of the element. Okay. So if you calculate like that, so ZP is area by 2. Area is what? If you take total area, there are two flanges here, 140 into 9 by 2 plus 35 into 35 here. If you take individually the areas, so first one, second one, third one, we calculate, you calculate area, then distance of centroids from this y line here also. So for these two, that is for these two elements, okay, here they calculated here. So carefully we should calculate the area into corresponding distances. Okay, if you calculate area into corresponding distances, we will going to end up with the plastic section modulus here 89.9 centimeter power 3. So there, this is a one more problem. The prismatic means what? The constant EI value. The beam is having constant EI. A prismatic propped cantilever beam of span L and plastic capacity M subject to constant load at midspan. The collapse load will be alpha MP by L. So what is this? This is a propped cantilever. We know already the answer is 6 MP by L. So many times they are asking this question. Here what they want, if the collapse load is alpha MP by L, then what is your alpha? The value of alpha will be, we should type here. What is your alpha value? The coefficient here is 6. So this is what the propped cantilever beam. Sometimes they may give figure, sometimes they may not give the figure. So we should write the propped cantilever beam. Okay. Then we should calculate the collapse load 6 MP by L. So here your alpha is 6. So now if you go for one more problem here, this recently asked question. The prismatic steel beam is as shown in figure. Okay. The plastic moment MP calculated for the collapse mechanism using static method and kinematic method is. So here if you calculate the static method and also kinematic method, okay, the MP static is they given 4 options here. Okay, the MP static is less than 2 PL by 9 equal to MP kinematic. So here if you calculate by using kinematic method, that is the mechanism method. Okay, so you're going to get the at collapse, this is what the internal work done, external work done. If you equate these two by calculating the alpha values here and phi values, you're going to get MP as 2 PL by 9. So in this case, if you observe, whatever the static method you apply on this beam, since it is a simply supported beam, whatever the static method, so definitely you're going to get the same answer as kinematic. So therefore, your answer here is option D is correct answer. So MP static equal to 2 MP 2 PL by 9 MP kinematic. So these are all the questions they ask it frequently on the plastic analysis. So the thing here is, in case of steel structures, we need to concentrate on the connections part, bolted and welded connection, and also the plastic analysis, and also the beams. So no need to study in detail the design of beams, the design of compression or tension members. So generally they will frequently asking questions on 2 marks questions on connection part, and also the the plastic analysis part. So you can concentrate only on these three problems: plastic analysis and connections part. So thank you. All the best for your GATE examination. Thank you.